Hello, this is John. Welcome to Fundamentals of Light and Lasers. This will be Lab 1-1B, and today we're going to determine the wavelength of red laser light using a diffraction grating. Okay, well, let's look at the equipment that we're going to use today. We're going to be using a laser that's aimed straight down at our screen, which is on the bottom. We're going to be using a diffraction grating. Ours happens to have 1,000 lines per millimeter. Yours may be different. And we're going to have a screen down at the bottom, which is simply a white piece of paper. We're going to be using a ruler that's calibrated in centimeters and millimeters. Now let me talk a little bit about how to set this equipment up, because there's a little bit of chance for confusion. The most obvious part is that we set up the laser shining down through the diffraction grating onto the paper, and the diffraction grating should be roughly 20 to 30 centimeters above the paper. However, if the diffraction grating is not perfectly horizontal above the paper, then the spacing of the dots in the diffraction pattern on the paper will be non-symmetrical. The center dot, which is the beam going straight through the diffraction grating, will not be equally spaced from the two patterns on either side. So measure with your ruler and be sure that they're both equally spaced. That will tell you that the diffraction grating is perfectly horizontal. So now we're ready to measure. We have two measurements to make in order to determine the angle that this diffraction grating is making with the pattern. First, we measure the vertical height. This one happens to be, looks like 21 centimeters, 21.0 centimeters vertically. And we're going to take the average of these two spacings, measure the center of these two dot patterns, and this one is approximately 18.3 centimeters on one side and 18.7 centimeters on the other. So I didn't do a perfect job of getting them lined up, so we'll take the 18.3. I'm going to go ahead and mark the dots on the page. 18.3 and 18.7, and the height was 21.0 centimeters height. Okay, now that we've got our data, let's analyze the data and find the wavelength of the light that produced our first order diffraction pattern. As the light went through the diffraction grating, it produced the first pattern. It was separated by a delta X from that center spot and formed an angle of theta. The angle theta is calculated by a tangent inverse of the geometry delta x divided by L. And our diffraction grating has a line spacing, in our case, of 1,000 lines per millimeter, which is equivalent to 10 to the minus 6 meters per line, or since we like to work in nanometers for wavelengths, then we'll say it's 1,000 nanometers. Now for our delta x, we measured 18.3 centimeters, and we measured an L of 21.0 centimeters. So if I calculate the ratio of 18.3 divided by 21 and take the inverse tangent, I get 41.07 for theta, 41.07 degrees for theta. And then if I put this into the formula for lambda, so I put in 1,000 nanometers for the spacing times the sine of 41.07 degrees, and we end up with lambda. The wavelength for our light is equal to 657 nanometers, which corresponds very well to the correct wavelength for our laser diode laser pointer. Okay, and that concludes Lab 1-1B. We'll see you next time.